Okay, so we are doing the second problem in this video, just going through another example of sampling proportions, or sampling distributions with proportions. So on this one, it says the cereal milk problem, the USA Today poll asked a random sample of 1,000 adults what they do with the milk in the bowl after they've eaten the cereal. A spokesman for the dairy industry claims that 70% of all US adults drink the cereal milk. So this would be our true proportion of adults who drink the cereal milk. Assume that this claim is true. What is the probability that less than 2/3 of the aforementioned sample drinks the cereal milk? So again, we know the proportion for all of US adults, which should be our population, and we're looking for the chances that a sample of 1,000 adults would have less than 2/3 of them, or less than 0.67 of them, who drink the cereal milk, based on that 70%. So our first step is to check our assumptions and conditions. So our first assumption is that we have a random sample, and that just makes sure that our sample is accurately representing the population. We were told that it was a random sample, so I'm going to say given random sample. Our second condition or assumption that we check is that we have independence between trials, or independence between each sample process. So because we are picking 1,000 adults probably without replacement, we do have to check this to make sure that our probability isn't changing significantly from one pick to the next, to the next, to the next. So what we would say here is that we assume, or it's safe to assume, that those 1,000 adults in our sample is less than 10% of our entire population, meaning our population is big enough that when we pick this 1,000 adults sample, that probability of picking someone who drinks the cereal milk isn't changing very much within that sample. So I'm going to say assume that 1,000 is less than 10% of all US adults. Our final condition, and this one's really more of a thing we do need to check, not just assume, is our check to see if our sampling distribution will be roughly normal, and that's where we check does n times p and n times 1 minus p both come out to greater than 10, or greater than or equal to 10. So n times p, well, n is 1,000, that's our sample size, p is 0.7, and 1,000 times 0.7 is 700. And then we're going to check n times q. Remember, q is just 1 minus p. It's just another shorthand. So if p is 0.7, 1 minus p would be 0.3. So 1,000 times 0.3 is 300. Both of those are greater than or equal to 10, which basically means that a normal model is the shape of our sampling distribution, which means that we can use a normal model to find a probability once we know our z-score. So that is our first step. Our second step is now to calculate the mean and standard deviation of our sampling distribution for samples of 1,000 US adults using the formulas that we have from our formula chart. So our first formula for the mean, mu p hat, is equal to just p, which is 0.7. Easy cheesy. And then our standard deviation formula, that was a really bad sigma symbol, my bad. Our standard deviation formula is square root of p times 1 minus p divided by n. So square root of 0.7, oops, almost set up 0.07, times 0.3 divided by 1,000. So I'm going to, real quick, put that in my calculator and see what we get. So from that we get 0.014. Again, keep in mind we are rounding right here, so it's just something to realize. We can just kind of use this whole thing in our formula a little bit when we find a z-score, but just know that the more decimals you use here, the more exact your final answer is going to be. I would go at least 3 decimal places always. So that is step 2. So now I'm going to move on to step 3, and I'm going to erase my assumptions conditions just to give myself a little bit more space here. So hold on while I do that. Alright, so now we are ready to do our third step, which is to calculate that probability using our normal model. Alright, our third condition passed, which means that our sampling distribution is roughly normal, and we have just found a mean and a standard deviation for this sampling distribution. So I'm actually going to start by kind of drawing what that sampling distribution more or less looks like, mainly that it's normal and that our mean in the middle is 0.7. So that is kind of the center of our distribution. We also know that the standard deviation is 0.014. So if I really wanted to, I can go ahead and, you know, put in the rest of the marks. I'm not going to, but we could. So then I'm going to find a z-score. And to know what z-score I need, I want to think about, I'm going to put in some probability notation of what it is I'm actually going to find at the end. So I want the probability that less than 2/3 of our sample. So I want that sample proportion p hat to be less than 2/3. That is my end goal. So 2/3 then is my observed value for my z-score. So I'm going to write z equals 2/3 is my observed value. Yes, you could round that to 0.67, but that's not exact, and so I'm just going to leave it as 2/3 as long as possible so that I get a final answer that's as exact as possible. So 2/3 is my observed minus 0.7 is my mean, divided by 0.014 is my standard deviation. Again, we could just put this whole little formula in the bottom part of that fraction and keep things more exact. And then we're going to find out what that equals. I'm going to put that in my calculator real quick. Hold on. So when I calculated my z-score in my calculator, and by the way, when I typed this top part in the calculator, I literally typed 2 divided by 3 minus. I didn't put any extra parentheses, I put parentheses around the entire numerator, but I didn't put any extra parentheses inside. The calculator knows to do the division first and then the subtraction, just a side note. But using the 0.014 versus using this whole fraction or this whole square root thing as the denominator actually made a pretty big difference in z-score. So if I use the whole fraction, I get a z-score of, negative 2.30, whereas if I use 0.014, I get a z-score of negative 2.38. So it's actually a fairly big difference. Even just putting one more decimal place right there on my denominator would have given me the negative 2.30. So it does make a difference. This is also why it's really important to show all of your work on these types of problems, because if you're getting like a different z-score or a different final answer, if I can see your work, I know where that number is coming from and I can verify that you're using the right steps and you won't get points off. Whereas if you just kind of leave things vague, it's really hard for me to give you that partial credit or even full credit for stuff like that. So just be careful, always show your work, always, but for this is one of the big reasons. So negative 2.3, that means this is landing 2 1/3-ish, so maybe right here, standard deviation's below the mean, so that's where 2/3 ends up being, that 0.67, that p hat that we are finding, and we wanted less than that, so I'm going to shade to the left, and then I would go look this up on my z-table. I'm going to go look that up real quick. And from my z-table, I get a probability of 0.0107. So that is my probability that our sample proportion would be less than 2/3. That less than 2/3 of a sample of 1,000 adults would drink the cereal milk if that 70% is true indeed for the entire population. So that is step 4, is to put that in some words. So I'm going to erase my mean and standard deviation just so I have space, and then I will write that out for you. So hold on. So there is our interpretation that there is a 0.0107 probability that a sample of 1,000 adults would have less than 2/3 of them who drink the cereal milk, assuming, of course, that that 70% is indeed the true proportion of all adults who drink the cereal milk. So that is how we do a problem like this. Thanks. See you later.